So this lecture is for February 17th. Well, we had a few requests for previous worksheets from whenever I was out. So it was really just this one worksheet here, front and back. All you're really having to do for all of these is look at your speed equals distance over time equation, which we can always use our little triangles here. I want to remind you that while speed is always going to be positive, it's going to be your distance over time. Velocity can be either positive or negative, and that it can be having a direction too, like north, south, east, or west. So that's going to be your main difference. So we do have in our previous lectures given a different equation for velocity, but this one is not going to have that because you don't have another acceleration. There's none of that. So you're really focusing on this right here. So speed equals distance over time. So let's look at our first question. Megan rolls a ball down a ramp until the ball hits the wall. The ramp is 2.5 meters long, and the distance from the end of the ramp to the wall is 1.5 meters. If it took 0.5 seconds for the ball to hit the wall, then what is the ball's speed? All right, so first off, you're going to look at what they gave you. Obvious one is our time, so we'll go ahead and highlight that one. The other one is talking about the distances that we have. Okay, Megan is simply rolling the ball down the ramp until it actually hits the wall. It is telling you that the total distance of the ramp is 2.5 meters, but in the end, it hit the wall, so you're going to be looking at right here, the 1.5. So we are solving for our speed. So that's what we would put right here, speed, or you can go ahead and put in an S, either way. We know that to calculate speed, speed equals distance over time. All right, this is to show your work. Distance is 1.5. Time is 0.5 seconds. So you would use your calculator. 1.5 divided by 0.5, and that gets you 3. Now, this last box is asking for answers with units. We already know that the answer is 3, so let's go ahead and look at the units. Our distance was measured in meters. Meters would go on top, and seconds is our time. So since time is on bottom, that means it should go on bottom. So meters per second, or if you wrote it out another way, M over S, it's the same thing. So either one. So our answer is 3 meters per second. So let's look at number 2. How much time does it take a person to walk 12 kilometers north at a velocity of 6.5 kilometers per hour? And again, you're able to tell here, it's asking for time. So you're solving for time, or t. You're given our values that we're going to look at right here, 12 km north, 6.5 kilometers per hour. And since we're solving for time, that means our equation is going to be a little bit different. So if you're using our triangle here, you would cover up t. You would know that time is equal to distance divided by speed. And so let's go ahead. Let's show our work. Distance is on top, so 12 is on top. And speed, which is what they have right here, 6.5 kilometers per hour. So 12 divided by 6.5, 1.85, 1.84, somewhere along those lines is fine. And then our units should be in seconds because our kilometers are canceling out. Now, again, this is where velocity is important. It gave you a direction. So the thing is, time isn't going to give you a direction, so north isn't as necessary here in the answer. So that's all we're doing throughout this worksheet is we're pretty much using this equation for everything, even on the back. So you just tell me, are you looking for time? Are you looking for speed? Are you looking for distance? Show me the equation, show me the work, and then give me the final answer with units. That's all it's asking for. So for today's assignment, we want to kind of introduce graphing. And I'm going to apologize in advance. I know drawing and graphing is a little bit difficult to do on the Chromebooks. So I completely understand if you would much rather do these on paper. I completely understand. Just make sure you take a picture of it and, submit it that way. So our first problem here, we are looking at an airplane that is descending to land at an airport. During its descent, it had to fly in circles until the landing was cleared of other planes. Explain what is occurring during each of the segments. Okay, I'm going to apologize. This is going to start sounding like a geometry class because we're going to be talking about line segments and everything else. So this question, they're giving you a scenario and they're wanting you to identify the parts of the graph. What do you think is actually occurring? So if an airplane is flying, so it's going to start at a higher distance because it's up in the sky, and it should be descending. That means it's going to be losing altitude. That means that distance is going to be lowering. So A to B, our line segment there, that's going to be our plane descending. And actually, let's write this over here off to the side. All right, so from B to C, nothing is happening here. It's not losing altitude. It's not gaining altitude. So you got to look at your scenario and what is the plane doing? It's not gaining or losing altitude. This is where it's flying in circles. So it's flying in circles. And then last but not least, we have line segment CD. The plane is finally allowed to cleared to land, and it is descending and landing. So this is all we're going to be doing here for these first couple of pages. We're just going to be going through these scenarios, and we're going to be identifying what parts of the graph we have. So for number 2, John left his home and walked 3 blocks to his school, as shown in the accompanying graph. So that means John started at home and he ended up at school. So this is the 3 blocks right here. We are looking for what is one possible interpretation of the section of the graph from point B to point C. So we're looking from line segment BC. So what could John have been doing here? As we see up here, again with the plane, we had that it was flying in circles, it was kind of staying still. it's the same concept once more. If you are staying still, that means that time is still progressing, but no distance has been made. So right here, that's where that flat line is coming from. So we have John arrived at school and stayed throughout the day. Okay, that would make more sense if the graph looked like this. But our graph doesn't look like that, so that's not really a possibility. John waited before crossing a street. I mean, that's a possibility. I mean, on his way to school, stoplight, had to stop. 3, John returned home to get his mathematics homework. So, looking at that, if John had left and then returned home, he would have had to return back, so that he would have lost distance. He would have had to go back towards the origin, and then he would have had to have left the house again. And our graph does not look like this. So that means 3 is not a possibility. 4, John reached the top of a hill and began walking on level ground. So graphs, they don't measure if you're on a hill or not. They measure the distance and the time. So if John was on the hill and began walking on level ground, you would have seen a straight line again. And our chart, our graph, does not look like that. So that looks like number 2, that possibility earlier, that's going to be our answer right here, number 2. So all these charts, all you're doing, going through them, identifying the pieces, what could possibly have happened. All right. Question number 3. Jen left her house and drove to school in the morning, as shown in the accompanying graph. On her drive to school, she realized that she forgot her book bag and had to return home before driving back to school for a 3-hour class. Explain what is happening during part of the graph below. All right, so we're going to be looking at all of our different line segments here. We're going to use the story that they gave us, and we're going to identify it. So AB, what's happening here? Look at your scenario. Jen left her house and drove to school. Increasing in distance, that makes sense. So Jen left her house and heading to school. All right, BC. She realized that she forgot her book bag and had to return home. So we're seeing that decrease in distance. So Jen went home. So Jen went home. CD. Once she got her homework, she began to head back towards school. So Jen is heading back to school. And then line DF, well, she's staying for a 3-hour class. So that's what we're doing right here. She's staying still. DF, she is staying for a 3-hour class. So here's our example there. So she left, she went back home, she left again, and she stayed for 3 hours. That's what we're looking at. All right, question 4. The accompanying graph shows Marie's distance from home to work at various times of her drive. So we're looking at our graph right here. Question A, Marie left her briefcase at home and had to return to get it. State which point represents when she turned around to go home. Well, just like with up here, when Jen went home, Marie, she's going back home. That should be line segment BC. It's showing that decrease. So the line is showing a decrease in distance. So that's what our arrow right here stands for. So BC, because the line is showing a decrease in distance. B, Marie also had to wait at the railroad tracks for a train to pass. How long did she have to wait? Well, remember, if you're having to wait, you're standing still. Standing still is that long line. And so we have that from points D to E. So we're looking at 25 to 30. And so our total time waiting is the difference. So 30 minus 25 equals 5. So she was waiting for 5 minutes. Right, this leads on to the next page. A bug travels up a tree from the ground over a 30-second interval. It travels fast at first and then slows down. All right, so we're going to pause right there. If the bug is traveling up a tree, we know that distance is being gained and not being lost. So that means choice number 2, right off the bat, is not possible. And choice number 4 is also not possible because you are looking for distance that is gained, not lost. Second, we are looking at a resting period. It travels fast and then starts to go slow. So there's a change in our speed. So 1 here would show a constant speed, but 3 shows that speed kind of slowing down. So let's just go ahead and double check. Let's keep reading it. It stops for 10 seconds. We see that right there. Then proceeds slowly speeding up as it goes. We see that right here. So that means choice number 3 would be our correct answer. All right, so these two for the next page, we already know that this is kind of like traveling to and from someplace, or walking up, going towards the kitchen, going back towards the bedroom, that type of example. Number 7 is what's probably going to catch you off guard. These kind of graphs represent a ball being tossed in the air, or someone jumping, because they're going up and they're falling back down. All right, so when we're getting into part 2 is going to be the actual homework that I'm looking at. We see a example of a dog walking around in a circle or something like that. When you are looking at a dog walking in a circle, you are looking at basically a circle that's cut in half. What you're going to see, if the dog is moving around, it is going to go up and down. Essentially, you are seeing those two halves make that full circle. So the dog is gaining distance and it's still walking, and then again it's starting to lose distance as it's going back towards its start. So if you're walking in a circle, this is our general graph that we should see. So part 2 right here, 4 graphs, 1, 2, 3, and 4. This is all I'm looking at for homework. If there's an extra page after this, I do apologize. You do not need to work on that last page. It is simply part 2, questions 1 through 4 that would be considered homework. Everything else that we did here, starting with problems 1 through 7, you can kind of keep that as notes. But that is about it. So if you do have questions, please feel free to email me or make a message on the assignment. But other than that, we don't have a Friday class, so make sure that you also enjoy your weekend.